Hey everyone, and welcome. Today we're doing a high-level review of Chapter 3, and we're going to focus on one of the most powerful tools in all of calculus, the derivative. So let's just dive right in. So think about this for a second. How do you actually measure something that's constantly changing? I mean, take a supercar like the Hennessy Venom GT. Its acceleration is not some steady number, it's changing every single split second. So how in the world do we pinpoint its exact acceleration at, say, the 7-second mark? Well, the answer, it's all in the techniques we cover in this chapter. And that's exactly where derivatives come into play. They are, without a doubt, the fundamental tool for understanding rates of change. And look, this isn't just about fast cars, right? This idea is absolutely critical in science, engineering, business, even in health. It's all about one thing, measuring how things change from one instant to the very next. Okay, so to really get a grip on these concepts, we've got to speak the language of calculus. We're about to run through the core terms from this chapter. I'd really recommend pausing as we go to make sure these definitions are locked in your brain. This first batch of terms, this is really the groundwork. You've got everything from acceleration, which is just the derivative of velocity, all the way to the core definition of the derivative itself, the slope of the tangent line. Honestly, understanding these is step one to unlocking everything else. Now, this next set of terms, it all kind of revolves around one central idea, being differentiable. It might sound like a fancy word, but it just means a derivative exists. And as you can see, we have different ways of talking about it, whether a function is differentiable at just one point, over its entire domain, or on some specific set. Okay, now we're getting into some of the more advanced techniques and, some really powerful real-world applications. We've got terms for higher-order derivatives. That's just taking a derivative of a derivative. And check this out. Key business terms like marginal cost, profit, and revenue, all of them are just direct applications of the derivative. So cool. And this last group of terms, these are the rules you're going to use all the time. The power, product, quotient, and sum rules, these are the workhorses of differentiation. Seriously, think of them as your shortcuts that save you from having to use that long, tedious limit definition every single time. So, with the language down, let's look at the tools. These are the key equations from the chapter. This is really the machinery that puts all that vocabulary into practice so we can actually calculate derivatives. This first group of equations really gets to the heart of the formal definition. Just notice how the difference quotient, the slope of the tangent line, and the derivative itself are all built on this idea of a limit. This right here, this is the bedrock of everything else in the chapter. Next up, we have the formula for instantaneous velocity, which is, simply the derivative of the position function. This slide also gives us our essential toolkit for trigonometry, laying out the derivatives for all the core trig functions. These are so fundamental, it's definitely worth taking a moment to review them. And here it is, probably one of the most important rules in all of calculus, the chain rule. This is our go-to tool for handling functions inside of other functions. This slide also introduces formulas for the derivatives of inverse functions, which is a really powerful application of these principles. Finally, we're rounding out our toolkit with the last of the inverse trig functions and, crucially, the rules for differentiating exponential and logarithmic functions. These are so essential for modeling, everything from population growth to radioactive decay. All right, with the vocabulary and the toolkit established, let's put it all together. We're going to walk through a quick summary of each section to see how all these concepts build on one another throughout the entire chapter. Section 3.1, this is where it all begins. The huge takeaway here is that the derivative is the slope of the tangent line, and that measures the instantaneous rate of change. This section just beautifully connects the geometric idea of a slope to the physical idea of velocity. Moving on to 3.2, we start to generalize this idea. See, the derivative isn't just a number at a single point. It's a whole new function, f prime of x, that tells us the slope at every point. This section also gets into the nitty-gritty of when a derivative might not exist. Section 3.3 is all about working smarter, not harder. I mean, once we understand the definition of a derivative, we don't want to use that long limit process every single time, right? So this is where we get our toolbox of rules, like the power rule and the product rule, that let us find derivatives way more quickly. In 3.4, we bring it all back to the real world. This section just brilliantly shows how the derivative of position is velocity and the derivative of that is acceleration. It also brings in those key business concepts we talked about, marginal cost, revenue, and profit. Section 3.5 is a really specialized but vital part of our toolkit. It focuses completely on the formulas for the 6 basic trig functions. And the really cool part is, once you have the derivatives for sine and cosine, you can use all your other rules to figure out the rest of them. Next up, Section 3.6 and the chain rule. This is arguably one of the most important differentiation techniques you will ever learn. This is our key to handling composite functions, functions that are nested inside other functions. It's an incredibly powerful and versatile tool. Building on our toolkit, Section 3.7 introduces the inverse function theorem. This is a super clever way to find the derivative of a function's inverse without having to start from scratch, and it's exactly how we find the derivatives for functions like inverse sine. In 3.8, we learn how to handle more complex relationships where you can't just easily solve for y. Implicit differentiation is the technique for finding the derivative in these cases, and it lets us analyze the slope of really complex curves like circles or ellipses. And finally, Section 3.9 rounds out the chapter with the rules for the functions that model so much of our natural world, exponential and logarithmic functions. It also introduces a great trick called logarithmic differentiation, which is super useful for simplifying really messy problems. So that's the chapter in a nutshell. We started with the fundamental definition of the derivative as a limit, we built up this powerful toolkit of rules, and then we applied them to all kinds of different functions and real-world scenarios. Which brings us right back to that Hennessy Venom GT. The tools from this chapter are exactly what you'd use to find its precise acceleration at any given moment. The derivative is the mathematics of change. So the final question I'll leave you with is this: where else in your world, beyond a textbook, is the rate of change happening right now?